Welcome students. Today we will study the last chapter from paper 1, that is radiation. You know that heat transfers from a body at high temperature to a body at low temperature, or inside a body heat flows from a point of high temperature to a point of lower temperature. Now this flow of heat from higher temperature to lower temperature is called heat transfer. Now heat can be transferred by three ways. The three ways with which the heat transfers are called modes of heat transfer. They are as follows. Conduction. It is defined as the mode of heat transfer through a material medium in which heat is carried from a point of higher temperature to a point of lower temperature without actual migration of the particles of the medium. Now, in this mode of transfer of heat, the particles are not allowed to migrate or to leave their position forever. Hence, this type of mode of transfer of heat is observed in metals. The atoms in metals receive heat from the preceding particle, then they vibrate with greater amplitude, and after completing the vibration, they transfer it or donate it to the succeeding particle. So this is how the heat is transferred from one point to another point. Hence, mode called conduction is mainly observed in metals. The substances which carry heat by the process of conduction are called conductors of heat. The substances which do not carry heat by the process of conduction are called bad conductors of heat. For example, water or ice are called bad conductors of heat. That does not mean they do not transfer heat. They do transfer heat, but not by the process of conduction, but by the other two processes. The second mode is called convection. It is defined as the mode of heat transfer through a material medium in which the particles of the medium physically move towards the source of heat or to the point of higher temperature and actually carry the heat away from the source to the point of lower temperature. Hence, the particles or the molecules are self-sufficient as far as the transfer of heat is concerned. For this mode, the molecules or the particles of the medium must be free to move. Hence, this mode of transfer of heat is observed in all the liquids and in most of the gases, including air. The third mode of transfer of heat is radiation. It is defined as the mode of transfer of heat in form of electromagnetic waves for which material medium is not necessary. Hence, for radiation, no medium is necessary, or radiation can transfer heat through vacuum. It is possible because the radiation is the mode of transfer of heat by electromagnetic waves which do not require any medium for their propagation. Radiation is by means of EM waves which travel with velocity of light. Hence, radiation is the fastest mode of transfer of heat. Now in this chapter we are going to concentrate only on radiation. Hence, the energy which we are going to consider is either absorbed or released or transferred in form of radiation only. Hence, it will be convenient to define what is radiant heat. Radiant heat is the heat in form of electromagnetic waves or infrared frequencies. As infrared frequencies are invisible, the radiant heat is also invisible. When the radiant heat is incident on a substance, it is partly absorbed, partly reflected, and partly transmitted, means allowed to go through it. Accordingly, some heat is absorbed, some heat is reflected, and some heat is transmitted. The efficiency with which the incident radiant heat is absorbed, reflected, or transmitted is measured by coefficient of absorption, coefficient of reflection, and coefficient of transmission. Coefficient of absorption A is defined as the ratio of incident radiant energy absorbed by a substance to the total incident radiant energy on it. That is, if IA is the incident radiant energy absorbed and I is the total incident radiant energy, then the ratio IA to I is called coefficient of absorption A. Hence, A is equal to IA upon I. Coefficient of reflection R is defined as the ratio of incident radiant energy reflected by a substance to the total radiant energy incident on it. Hence, if IR is the incident radiant energy reflected by a substance, then R, that is coefficient of reflection, is given as IR upon I. Coefficient of transmission T is defined as the ratio of incident radiant energy transmitted by a substance to the total incident radiant energy. Hence, if IT is the incident radiant energy transmitted by the substance, then coefficient of transmission T is IT upon I. It can be proved that the sum of all these coefficients is 1. That is, A plus R plus T is equal to 1. As far as transfer of heat is concerned, the substances are classified into two types: diathermic substances and athermonous substances. Diathermic substances or diathermonous substances are the substances which allow the heat radiations to pass through them. Hence, the substances which allow the heat radiations to pass through them are called diathermonous substances. For example, glass, quartz, all gases, etc. When heat is incident on them, they allow some heat to pass through them. There are some substances which do not allow the transmission of heat. They either absorb the heat or reflect it. Such substances are called athermonous substances. Hence, the substances which do not allow the heat radiations to pass through them are called athermonous substances. For example, all metals, wood, water, etc. These substances mostly absorb the heat and reflect some part of it, but in any case do not allow the heat to pass through them. Now, can there be any body which will absorb all the incident radiant heat? The answer is yes. It is called perfectly black body. A body which absorbs all the incident radiant heat is called perfectly black body. Thus, for such a body, coefficient of absorption is 1, and obviously the coefficient of reflection and transmission are 0. Actually, no such body exists in practice, but lamp black absorbs 98% of the radiant heat incident on it. Hence, for all practical purposes, lamp black can be considered as a perfectly black body. Now, it is very essential to define the emissive power of the body and the emissive power of the given body as compared to a standard body, which is nothing but a perfectly black body. Accordingly, two very important definitions are emissive power E and emissivity or coefficient of emission small e. Emissive power E is the quantity of radiant heat emitted per unit time per unit area of a body at a given temperature is called the emissive power E of the body at that temperature. Hence, if Q is the radiant heat emitted by a body of area A in time t, then the emissive power is given as Q upon AT. The SI units of emissive power are joule per square meter second, or joule per second can be replaced by watt, hence watt per square meter. Now, how to decide whether this emissive power is large or small? Hence, the emissive power of the given body is always compared with emissive power of a perfectly black body, and the ratio is called emissivity or coefficient of emission E. Emissivity of any body for a given wavelength of radiant heat is defined as the ratio of emissive power of that body to the emissive power of a perfectly black body at the same temperature. Hence, if EB is the emissive power of a perfectly black body, then E is equal to E upon EB. Prevost's theory of heat exchange has its important role in the thermodynamics. There are two main postulates of Prevost's theory. The first one is every body radiates heat at all temperatures except absolute zero temperature. And the second, the rate of radiation depends on the absolute temperature of the body, nature of its surface and its area. The rate of radiation is independent of temperature of the surrounding. According to Prevost's theory, there can be three cases in which the body radiates heat as well as absorb heat. The first one, when a hot body is kept in cold surrounding, then it emits heat as well as absorbs heat as per Prevost's theory. But this time the emitted heat is greater than the heat absorbed, or the body loses more heat and gains less heat. So there is net loss of heat of the body, which decreases its temperature. The process continues till the temperature of the body becomes same as that of the surroundings. In the second case, if you keep a cold body in hot surroundings, then also the body is going to emit heat as well as going to absorb heat. But this time it is going to absorb more heat than it is going to emit. Hence, there is net gain of heat, which is going to increase its temperature. Hence, the temperature of the body increases till it becomes same as that of the surroundings. When the temperature of the body and the surroundings both are same, means a body is neither hot or cold, then it absorbs heat as well as emits heat. It absorbs heat as well as emits heat. This time the energy absorbed is same as the energy emitted. Hence, there is neither gain or loss of heat, or heat of the body remains constant. Hence, its temperature also remains constant. This is how, according to Prevost's theory, we can explain why the temperature of the body increases when it is kept in hot surrounding, why the temperature of the body decreases when it is kept in cold surroundings, and why temperature of the body remains constant when it is kept in the surroundings of the same temperature. Making good use of Prevost's theory, scientist Kirchoff stated his law, which is known as Kirchoff's law. At any given temperature, the coefficient of absorption of a body is equal to its coefficient of emission. Thus, A, that is coefficient of absorption, is equal to E, that is coefficient of emission or emissivity. But E is equal to E upon EB. Therefore, A is equal to E upon EB, or very important, E upon A is equal to EB. Kirchoff's law can be also stated as the ratio of emissive power E to the coefficient of absorption A of a body is same for all the bodies at the given temperature and is equal to the emissive power EB of a perfectly black body at that temperature. Hence, as the amount of heat absorbed increases, A increases. In order to keep the ratio E upon A constant, E also increases. Means when a body absorbs more heat, it emits also more amount of heat. Hence, a good emitter is good absorber also. One of the statements from Prevost's theory was surprising, that the rate of radiation is independent of temperature of the surroundings. But it was also stated by scientist Stephen in Stephen's law of radiation. According to the law, the radiant heat emitted per unit time per unit area of a perfectly black body is directly proportional to fourth power of its absolute temperature. Hence, if Q is the quantity of radiant heat emitted per unit time per unit area by a perfectly black body and capital T is its absolute temperature, then Q is proportional to T raised to 4, or Q is equal to sigma T raised to 4, where sigma is called Stephen's constant. The value of Stephen's constant is 5.67 into 10 raised to minus 8 joule per square meter second Kelvin raised to 4, or 5.67 into 10 raised to minus 8 watt per square meter Kelvin raised to 4 in SI, and 5.67 into 10 raised to minus 5 erg per square centimeter second Kelvin raised to 4 in CGS. Now, equation number 1 can be written as EB is equal to sigma T raised to 4, because LHS is the amount of heat emitted by a perfectly black body in unit time per unit area, means it is EB. For emissive power of an ordinary non-black body at absolute temperature T, you have to substitute EB by E into EB, because we know that E upon EB is equal to small e. Hence, E is equal to E into EB, where E is coefficient of emission or emissivity. Hence, E is equal to E sigma T raised to 4. This expression gives radiant heat per unit time per unit area by an ordinary body at absolute temperature T. Now look at these two formulae. In these two formulae, the temperature of the surroundings is not mentioned. Means the amount of heat radiated is independent of the surrounding temperature. However, the rate of loss of heat depends on the surrounding temperature. The rate of loss of heat by ordinary body per unit area is given as dq by dt is equal to E sigma T raised to 4 minus T naught raised to 4. For area A, it is given as dq by dt is equal to A E sigma T raised to 4 minus T naught raised to 4, where T naught is the absolute temperature of the surroundings. Hence, the rate of emission is independent of surrounding temperature, but the rate of loss of heat, or the rate at which the heat is lost by the substance, depends on the surrounding temperature. Now, extension of Stephen's law of radiation, or the special case of Stephen's law of radiation, in which the temperature of the body is not much high than the surrounding temperature, is Newton's law of cooling. Hence, Newton's law of cooling is called special case of Stephen's law of radiation. The rate of loss of heat from a body is directly proportional to the excess temperature of the body over the surroundings, provided that this excess is small. That is, dq by dt is proportional to theta minus theta naught, or dq by dt is equal to k into bracket theta minus theta naught, where k is a constant. Now, the statement is similar to the statement of Stephen's law of radiation. Hence, dq by dt is k into bracket theta minus theta naught. The statement can be rewritten in the other words also. If you replace dq by dt as ms d theta by dt, then it can be stated as the rate of fall of temperature of a body is directly proportional to the excess temperature of the body over the surroundings, provided that the excess is small. That is, d theta by dt is proportional to theta minus theta naught, or d theta by dt is equal to k upon ms into bracket theta minus theta naught, where k upon ms is also a constant. Newton's law is valid for excess temperature theta minus theta naught to be equal to or less than 30 degrees Celsius. If the temperature of the body is more than 30 degrees Celsius over the surroundings, then the Newton's law cannot be used, or in that case Stephen's law of radiation should be used. Now, last two very important points for CET in this chapter are Wien displacement law and solar constant. According to Wien displacement law, the product of maximum wavelength corresponding to energy, that is lambda m, and the absolute temperature T of the body is constant. That is, lambda m into T is constant, which is called Wien constant B, whose value is 2.88 into 10 raised to minus 3 meter Kelvin. From this law, it can be seen that a body at higher temperature emits the energy of lower wavelength, and a body at lower temperature emits energy of higher wavelength. From this, you can also calculate the absolute temperature of the surface of the sun and absolute temperature of the core of the sun. From core of the sun, we get the high frequency light or low wavelength light. From the surface of the sun, we get low frequency light or higher wavelength light. Similarly, solar constant, it is defined as the quantity of solar energy received per unit time per unit area of the earth in the absence of atmosphere, when this area is held right angles to the incident radiation at a distance equal to mean distance of the earth from the sun. Its value is around 1340 1340 watt per square meter. It is defined because one should know how much energy we receive per square meter area from the sun. Fortunately, it is constant all over the surface of the earth, but it changes according to the atmospheric conditions such as presence or absence of clouds, sunspot cycles, etc. Otherwise, the value is more or less constant.